So there's one detail we have left hanging regarding the formula that we came up with for finding a surface area of rotation, and that is this idea that when you have a cone, right, when we rotated a bit of arc length, we got this bottom band of a cone, and we sort of guessed a formula for what the area of this sort of thing should be. But, you know, even though the guess is plausible, it's still a guess. And so we really should justify why it came out to be what it is. So this shape, this bottom band of a cone, is called the frustum of a cone. So that's what this refers to. It seems like before we jump into finding the surface area of the band around the bottom of the cone, maybe we should just find the area of a cone first. So we have a cone, circular base like this. Okay, with the cone, there's a radius around the bottom. And you need one more measurement to sort of fix the dimensions of the cone that you're talking about. You might use the height, but it's actually a little more convenient to use this sort of side length. So I'm going to call that capital L. So how to find the surface area of this cone? Oh, incidentally, we're going to find the surface area of just the top sides of the cone, not the circular bottom. We know the area of the circular bottom, so we're just going to find the area of the top. So it's a little hard to know what to do, but you know, if you think about how you make a cone out of paper, say, you take some sort of shape like this, and you glue two edges together to get a cone. So the cone that you would produce from this sort of shape has a seam down the side, right? In fact, let me draw that in blue. So this seam down the side matches up with this blue length, and it's glued together with this blue length. Okay. But if you think about it, this blue length on our cone, that's exactly the length down the side of the cone, but we called that L. So this blue length is capital L. But that means over here, where we've sort of split our cone apart and laid it flat, this length is L, and this length is also L. What about the red around the outside of this laid flat cone? Where did that come from in the picture? Well, it's actually around here. Right? If you take this shape and imagine gluing these sides together, the red around the outside turns into the bottom of the cone. But we know how long that is because it's a circle, and the radius of that circle is little r. So this red circumference here is 2 pi r because it's the circumference of a circle. All right. So, all right, we're making some progress here because this red distance is 2 pi r, little r, and we have the radius of this circle, it's capital L. So the area that we want is everything in here, right? Which is the area of a circle, except we've cut out this wedge. So what we need to know is how big is this angle here? If we know this angle, then we can figure out what fraction of the circle we actually have. So let's call this angle theta, I guess. So to find theta, we're going to have to, let's see, relate, make some relationship between sort of the circumference of the entire circle and the piece of the circumference that we have right here. So when you have only part of a circle like this, the distance around the outside, so we called this C over here, the distance around the outside, on the one hand, we have a formula for it. It's 2 pi r, and that's coming from the cone. On the other hand, when you have part of a circle, the arc of a circle is the radius of the circle, which for this big circle that we don't have all of, the radius is actually L, times the angle at the inside, which is theta. Okay, well look, we can set these equal, since both of these are C, we can set these equal to each other. So theta is 2 pi r, and then we can find L if we want. So, sorry, I've left off an L here. I need an L. So then we can find theta. Theta is 2 pi r over L. Okay, and then the area of part of a circle, right, this area, the area of just part of a circle is 1/2 the angle times the radius squared. And the radius of this big circle is L. So 1/2 theta L squared. But we just found theta, so let's put that in. So theta is 2 pi r over L times L squared. And then when we simplify this whole mess, we get the area is, right, the 2's cancel, one of the L's cancel, we get pi times little r times capital L. So this is the side area of a cone. Okay. Good. So that seems like a good place to start, right? We're going to find the band around the area of the band around the bottom of the cone. So finding the area of the whole cone is a good place to start. So now let's go back to the frustum of a cone, the band around the bottom. So we have, this is the part of the cone that we have. And then this dotted part above is the part of the cone that's missing, the part that we've cut off. And you see there's actually two cones here, right? There's the whole cone, and then there's the missing cone that's at the top. So the whole cone, its side length is like this. Let's call that L1, so the first side length. The missing part of the cone at the top is also a cone, and let's call the side length there L2, I guess. And of course, each cone has its own radius. So the big entire cone has a radius. Let's call that R1. And then the missing cone at the top has a radius. Let's call that R2. Okay, so the area that total area of the frustum of the cone, so area of the frustum, so A sub F, I guess, area of the frustum is the area of the entire thing, so whole cone, minus the area of the top cone, which is the part that we've cut away up at the top here. So the area of the whole cone, well, it's a cone, so we can use our cone area formula here. It's pi times the radius of the whole cone, which is R1, times the side length of the whole cone, which is L1, minus the area of the top cone, which is pi times the radius of the top cone, which is R2, times the side length of the top cone, which is L2. Okay, so this is progress, but it won't really help with our surface area of rotation measurement, because to use this we would have to know these lengths, and in the context of a surface area of rotation we don't know those lengths. It's possible we could find them if we worked hard enough, we could, but there's another way to get around it. So our goal is going to be do some sort of trickery to get rid of the L's, because in the context of the frustum of a cone, we won't really know these lengths. What we'll know is the difference of these lengths, which is this red distance here, right? So we don't really want L1 and L2 to show up on their own. We only want to want L1 minus L2 to show up, and we don't have that yet. So let's see what we can do. There's a pi to factor out, so let's factor out the pi. The pi times R1 L1 minus R2 L2. Okay, so the way that we're going to do this is with a little bit of trickery, and it's going to involve some similar triangles. So if you look at this cone, there are some similar triangles right here. Right, so there's that big blue triangle and this small red triangle. Okay, and so we can use similar triangles to relate the R's and the L's. And the way that I'm going to do this is, so R1 over L1, so the radius over the length for the big triangle, by similar triangles, that's equal to the small radius over the small length. Okay, so the fact that these two are equal, these two ratios are equal, is sort of a key thing for this whole situation. So I'd like R1 over L1 and R2 over L2 to show up over here because I happen to know that those are equal. And we can make them show up, right? Here's an R1 right here. We can make it B over L1, but to compensate, we have to have another factor of L1, right? So I've sort of intentionally unsimplified here, just so that I could have R1 over L1, right? But this is equal to what's directly above it, because you can just cancel an L1. We can do the same thing for the R1 and L2 part, so R2 over L2 times L2 squared. And R1 over L1 and R2 over L2, remember those are equal. So these two pieces, here and here, are actually a common factor, so we can factor those out. They look different, but actually we know that they're equal because of similar triangles. So R1 over L1, right? Both of these are equal to R1 over L1, so I'll factor that out. And that leaves behind L1 squared minus L2 squared. Well, look, now we have a difference of squares. I hope you have some sort of something deep inside you that when you see a difference of squares, you demand that it be factored. And we can factor this. This is L1 minus L2. Sorry, I want the plus first. So it's L1 plus L2 times L1 minus L2. Okay, well look, there's L1 minus L2. Remember, up on our cone, L1 minus L2 is actually this red distance, which is the length of the side length of our frustum, so L1 minus L2. So having L1 minus L2 is okay, because that's, if we have a frustum sitting in front of us, we can measure L1 minus L2. So we're happy having L1 minus L2 in this formula, but what we aren't happy with is L1 plus L2, because if we had a frustum sitting in front of us, we couldn't measure L1 plus L2. So we'd like to somehow, deal with this. And here's what we can do. I know we just factored out R1 over L1, but now let's multiply it back through just this piece. So you get R1 over L1 times L1 plus R1 over L1 times L2 times L1 minus L2. Okay, in this first term, the L1s cancel, and you just get R1. In the second term, remember, R1 over L1 is equal to R2 over L2. So we can replace R1 over L1 with R2 over L2 times L2 times L1 minus L2. And now we can cancel the L2's. And we get pi times R1 plus R2 times L1 minus L2. So this is the area of a frustum of a cone. And all of these things that show up in this formula are things you could measure if you had a frustum sitting in front of you. So here's a frustum, right? This difference, L1 minus L2, is the side length, and you could measure that. R1 is the radius of the bottom, and you could measure that. And R2 is the radius of the top, so you could measure that. So this is sort of an indication that this way of writing the area of a frustum is good, because you can find all of the pieces of it just if you have the object sitting in front of you. All right, so finally we know the area of the frustum of a cone. But remember, why did we get this formula? It was because we wanted to know the area of a band that you get when a bit of arc length gets rotated. So here's, right, if we have some graph, y equals f of x, at a position x, we have this little bit of arc length right here. And the length of that is ds. And when this is rotated, it sweeps out a frustum. Right, that's the key thing here. It sweeps out a frustum. So there's our frustum. In fact, we can even see the other piece through there. Okay, so all we need to do to find the area of this band is use our area formula for a frustum. So the area here is pi times the big radius. So, well, look, we need to be a little more careful about this x value. So let's say this x value is right here. The other end of this bit of arc length is at this next door x value, which is x plus an infinitely small bit in the x direction, which is dx. Okay. So R1, the big radius, is x plus dx. Okay, plus R2, the small radius, I'm sorry, that's not right. The x value here is x plus dx, but the height, this radius, is in the vertical direction, so we need to apply the function to this x value. There we go. Okay. Plus. So the small radius on this frustum is the function at the left-hand x value, which is x, so f of x. Okay. And L1 minus L2, that's the side length of the frustum, but that's ds. Okay. So, sorry, ds, not dx. Okay. So this is pi times. So what about this f of x plus dx? Well, f of x plus dx is f of x plus df dx times dx. This is essentially the definition of a derivative. Okay, plus f of x times ds. So we get pi times, now we have two copies of f of x, so 2f of x. While I'm at it, I'm going to distribute my ds into this thing, so times ds plus df dx times dx times ds. Okay, and now here's one key insight about calculus in general and differentials in particular. When you're working out some quantity and it has a differential times another differential, so right, if you compare the size of these two things, they're both infinitely small because the first one has a differential in it, so it's infinitely small. The second one has two differentials multiplied together, so it's sort of doubly infinitely small. So it's so small that it doesn't matter. So we're just going to cross it out. Now there is a technical justification for this, which is, really all of these quantities that I'm representing with d's, we can approximate them with small bits, in which case we'd write them with deltas, and then we'd take some sort of limit. And when you do that, this limit just goes to 0, and this limit on the left doesn't. So that's the technical justification. Well, that's a description of the technical justification. But since this part is sort of doubly infinitely small, so we can neglect it, we get 2 pi times f of x times ds. And that's exactly the formula for the area of one of these bands that we guessed when we developed our surface area of rotation integral. So this formula that we guessed really is right, even though it took a lot of work to see it.